Yeah, you should be finished. You're also going to be recorded from now on. Yeah, so it shouldn't take longer than an hour in the final, and yeah, you should be finished by approximately 1. Good. So as said, today we're going to talk about the only non-parametric test we're going to be doing, which is the chi-squared test, which is a fun test. I think you're going to like that one. It's kind of interesting, and it's very practically oriented. You will need this test in quite some context. Then next week on the 27th. I thought it was the 29th. Would you rather do it on the 29th or on the 27th? I'm fine either way. It's a study day on the 29th, and I think there's a Tuesday schedule, right? But I'm open to do it on Monday, in case you prefer Monday. I think the Zoom is scheduled for 29th, and I think we talked about the 29th. I just want to do one review session. So let's stick with the 29th. Let's actually do it on Wednesday. I would prefer that, if that's okay, if there's no conflict. Let me know if any conflict. I just want to go over the entire material with you just in a very quick fashion. Then also happy to do a quick Excel review session. Let me know when this would work for you. Would that maybe be something for Monday? Would you be available on Monday the 27th in the evening for like a quick walkthrough through Excel?
Wait, is this in addition to the final review?
Yeah,
or
yeah,
instead?
no, but this would be voluntary. So there was some discussion that this would be helpful for some of you to do kind of an Excel crash course where I kind of would walk you through the ins and outs of Excel. So really focused on Excel more than anything else. I think some of you
record it.
Yes, this session is recorded. I can also record the Excel session. Yeah.
Okay, thank you.
Sure. Okay, so I will schedule it for the 27th. I will. I hope some of you can join. It's a little bit more fun to teach something like that when it's interactive. So we're there. Okay, so we are talking today about the chi-squared test. Let me just quickly get this sorted out with the screen. Okay, so we're going to do some calculation. Please also download the spreadsheet. So we're going to do some calculation to essentially accompany what we're discussing today. So the chi-squared test. So this is the only non-parametric statistic that we will be discussing. It's a special class of a hypothesis test that essentially allows to associate to test for associations between counts. So we will see what that essentially means. Okay, so non-parametric statistics are basically used when you do not have to make any assumptions about the distribution. It's mainly about the distribution, but there are other reasons why you could not use parametric tests that are based on normal distribution and data that is normally distributed. So, so essentially the assumptions, as said, it's the assumptions for a parametric test is normal distribution. It's with a regression, for example, it's linearity in your correlation. It's also an independence of in the individual entries. And lastly, but certainly not least, it's the so-called homoscedasticity, which is essentially what we have discussed in the context of regression and in the context of ANOVA, where basically the variance between the groups shall not differ more than a certain amount, which is usually for ANOVA, it's recommended to not exceed 20%. So essentially, you distinguish between pattern and chance when observational data does not have a scale-dependent variable. So that means that there are differences between the tests that you will be using for different use cases. So we talked quite in much detail about a nominal independent variable, where you basically have groups, nominal or ordinal, on the x-axis, and you have a scale-dependent variable on the y-axis. So one of the tests that we discussed first was the SET test, then where you knew the population mean and the, bless you, then you also knew the standard deviation from your population, to which you would essentially use them to calculate your SET test. The t-test, the main difference between t-test and SET test is that the standard deviation is not given, and you will calculate or estimate the standard deviation of the population based on the standard deviation in your sample. And you will, for that purpose, the difference will be that the division by sample size that you would do for the population, you will use the degrees of freedom instead, where you subtract 1 from the sample size. Further, you have, as another example, we have a nominal independent variable and a scale dependent variable. You have the ANOVA. So the ANOVA, you basically have 3 or more groups, and you're using the ANOVA to get one global hypothesis test, where basically you are comparing the groups versus each other. And this is essentially, again, nominal independent variable and scale dependent variable. The only 2 tests that we discussed that essentially use a scale independent variable and a scale dependent variable is correlation and regression, which we have discussed quite extensively over the last 3 classes. So, and now we're adding a new one. Now we're adding the chi-square test. So non-parametric tests, you have different non-parametric tests that they can be using. The chi-squared kind of joined the party for the introductory course because it's basically the only, it's the only test we're discussing where basically you can work with a dependent variable that is nominal and an independent variable that is nominal. So when the dependent variable is nominal, this is the first time where we were discussing such a case. So what does that mean? So you can use it when the dependent variable is nominal, the dependent variable is ordinal, which comes to the same end, it's ordered. And then when the sample size is small and the underlying population is not normal, therefore violating one of the main rules of employing a parametric test. So what you do in this case is you're using the chi-squared test. So the problem which starts is that you don't have confidence interval in effect size measures for nominal and ordinal data. So when you're essentially looking at ordinal and nominal data, you would not easily get confidence intervals out of your data. So you want some form of variability, and you get this with a chi-square test. Non-parametric tests, and this is the caveat with non-parametric tests, they have less statistical power. Therefore, non-parametric tests are not preferred over parametric tests. So as said, you have parametric test, you have a t-test, and you have a corresponding non-parametric test, which is not based on a normal distribution. So if you have a sample size that exceeds 30, with these magic numbers by statisticians used to essentially allow for parametric testing despite not a clear normal distribution, you would prefer always the parametric test over the non-parametric test because they have less statistical power. As a consequence of that, you're more likely to commit type 2 error with a parametric test. So what is a type 2 error? So can one of you maybe remember what a type 1 or a type 2 error is?
It's either like false positive or false negative. I forgot which is which.
Yes, the type 1 error is the false positive, correct. So you're rejecting something which you shouldn't have rejected. Very good, Evie. And the type 2 error is an error where you have not rejected what you should have rejected. And the resulting power is essentially the type is 1 minus the type 2 error. This is the power that you essentially have in your statistical test to not commit such a type 2 error. So 1 minus the type 2 error is the power. So if the power is smaller, your type 2 error probability increases. So this is to be kept in mind with non-parametric tests. So now the chi-squared test, as said, you have a dependent variable that is not scale dependent. meaning you have one nominal variable for a chi-square test for goodness of fit, which is only one with two different groups. And you have a chi-square test for independence, where you have two nominal variables as your outcome variable or your dependent variable. And we will calculate both, and they basically follow the same kind of principle, and they're really super easy. So, yeah, we have discussed this quite extensively. So non-parametric test with a nominal variable. You have 6 steps of hypothesis testing. You have to identify your populations, your distributions, and assumptions. You have to state hypothesis, determine characteristic of the comparison distribution, determine the critical values, calculate, and decide it. So it's again the same 6 steps that you will be employing, and you always have 2 populations. And you're working now with frequencies. So it's a nominal variable. So if you remember the frequency tables, and that was the volcano example where we counted volcanoes for the countries. So if you have frequency rather than an independent measurement of some other sorts that essentially is attributed to each individual, and by that you get a scale dependent variable, you will now work only by counting occurrences or individuals or whatever you want to count. So these frequencies that actually had been observed are now compared to frequencies that are expected based on your null hypothesis. And you will see in a second what I mean by that. So the comparison distribution, so you compare again, you quantify some value, which is the chi-squared value. And this chi-squared, you're again comparing against a distribution that is just, if you remember with the ANOVA, with the ANOVA, we got one F value, and we compared this F score against a unimodal right-skewed distribution and a critical value that we have found on this right-skewed unimodal distribution. Once your F score, or in the very same example for the chi-squared distribution, exceeds that critical value, we essentially reject the null hypothesis. So the same principle as we had with the F score. So again, we're calculating chi-squared by basically comparing the frequency of the observed participants to the frequency of participants as it would have been expected. This comparison distribution we're employing is the chi-squared distribution. We have a nominal variables. They're all independent observations. This is central. This is one of the observations that actually, this is one of the assumptions that are actually very important for non-parametric tests, is that it's all independent observations, so you can't double count an individual. You have a random selection. So there's no differences. So there's no bias, so to say, why individuals were chosen, and you have a minimum number of expected participants per cell, which differs in the recommendation, but definitely do not do the test when you have a cell size smaller than 5, I believe was one of the values. So you should definitely not touch it when there's a cell size smaller than 0 or smaller than 1. So additionally, for the determination of the critical value, just like with the F test and the ANOVA, we essentially need to determine the degrees of freedom. With degrees of freedom for the rows, degrees of freedom of the columns. So when you are essentially thinking now of a frequency table, you have row and columns. And if we are opening now quickly, okay. So here's module 25. That's our in-class calculations spreadsheet, which you have in your module. An example of how you can look at this. So this is this example on the second page. So this is essentially these cells that I'm referring to when I talk about cells. So this is the example we're going to do later. So right now we're only working with one nominal variable. But this is essentially, these are degrees of freedom row degrees of freedom column. So this is a so-called contingency table where you basically quantify counts in certain groupings. So you would determine the characteristics of one cell by basically coming from top. Usually this is the outcome. This is your dependent variable. And on the rows, you essentially have the independent variable. So you can use this for this example that we will discuss later on, or you can use this for diseases. So this would be disease positive, disease negative in my realm. This would be exposure. If this were lung cancer, yes, no. This would be smoker, yes, no, for example, as an example. Here's a different example. But basically, so all these cells essentially are resultant of following along with row and columns. So these are the cells we're talking about. So now we have our first example, but let's finish the slides for now. So we have degrees of freedom K is the number of rows. So if I have 3 rows, I have a K row of 3. Minus 1 is 2. If I have a K column, is the number of columns. Minus 1 gives me the degrees of freedom of column. If I want to calculate the degrees of freedom of my chi-square statistic, I essentially take the degrees of freedom of the row, multiply them with the degrees of freedom of the column. So for putting this into practice, so degrees of freedom row, for this example, we have 3 rows. So our degrees of freedom here is 3 minus 1 is 2, right? So degrees of freedom column here is 1 and 2, minus 1 is 1. So the degrees of freedom chi-squared for this example with 3 rows, 2 columns is 2 multiplied by 1. Yes, Amira?
Would you be able to zoom in a little bit? It's hard to see the numbers.
Sure. I'm already on the big screen. I hope that was better. How's that? Yep, good. Okay, so 3 rows, 2 columns. 3 rows minus 1 is 2, multiplied by 1 is 1. So the critical value, and I'm walking ahead a bit. So this is the chi-squared probability table. We have here on top, we have again the probabilities, so the so-called p-values. These are our thresholds. So we want 5%. Degrees of freedom of chi-squared is 3 minus 1, 2, multiplied by 2 minus 1, 1 is 2. So our 5% critical value is 5.99 chi-squared. Okay, simple, not complicated. So this being said, let's get started with the first example, which is not this one, which is 17.1. And okay, yeah. So this is an accept that Nolan and Heinzen have chosen here. So this is, we have for a degree of freedom of 1, which is actually on the one I just showed you, is not even depicted because the goodness of fit. So there are different ways than the goodness of fit. It's usually you wouldn't use a chi-squared for just one nominal variable, but that's a different conversation piece. So for a degree of freedom of 1, the threshold is 3.841. So keep this number in mind, because now essentially we are coming to our first example. So this is the chi-squared distribution. Unimodal, right or positively skewed, with a threshold somewhere on the right tail. And this is our 5% critical value. Good. The area under this curve beyond this 5% critical value is summing up to 5%. Good. So now we're getting to our example. And this is the formula for a chi-squared. This is the only formula you need to, or you don't even need to recognize it because it's an open book final exam. We are looking at chi-squared equals the sum of observed minus expected squared divided by the expected count. So what does this mean? So you have, here the example. So you have Researchers reported that the best used soccer players in the world were more likely to have been born early in the year than later. As one example, they reported that 52 elite youth players in Germany were born in January, February, March, whereas only 4 players were born in October, November, or December. Those born in other months were not included in the study. Quite debatable study, I have to say, but okay, let's take it for now. Okay, so we have first 3 months, then we have the last 3 months. So we have observed.
Sorry, can you zoom in again?
Absolutely. Yeah. Better?
Tiny bit more, maybe. I just want to.
Well, I'm trying to expand here. I need a little bit of playground here. Okay. How's that?
Yeah, that's good. Thank you.
Super? Okay, good. Thanks for the reminder. I chronically always go for smaller. Okay, so we have observed and we have expected. And we have, during the first 3 months, we have 52 elite youth players that were born. So this is 52. Then we have the last 3 months, only 4. So we want to know now whether there's actually really a difference, a significant difference. So what would you expect under a null hypothesis that there's no difference? When you have a total of, so you also always quantify the so-called marginal total, which is here in this case 56. So if you were being asked, okay, so you don't see a significant difference, there's no difference between first 3 months and last 3 months, what would be your response? How many would you expect to see in the first 3 months?
Would be the same numbers.
Yes, yes. But in terms of distribution, how many youth players would you expect in the first 3 months or in the last 3 months? It should be 50% in each, right? Should be 50-50, or maybe just 50%, whatever works. So essentially we have now 28 and 28. Sums up to the same marginal total, right? So this is a probability of 50%, which essentially means this is like tossing a coin, whether this individual becomes a professional football player or not, which I believe essentially is the case. But that's a different conversation piece. Okay, so now we have observed and expected. What do we need now? Now we need observed minus expected squared. So this is then O minus E squared, right? So this is observed. Oh, don't forget the parentheses, please. So this is observed minus expected squared for both. Let's put this one. Hmm. It's a little confusing, but okay. Okay. So if we are now, okay, so we have observed minus expected divided by squared. So now we need to divide this by our, so now we're coming to O minus E squared divided by expected, right? So this essentially is now, let's put the parentheses just to make sure it's being recognized. So now this being said is now this divided by expected. It's now 20.571. And this is equally true for the second one. Okay. So this is just a coincidence that it's the same observed minus expected squared, because 52 minus 28 is 24, and 4 minus 28 is minus 24. Squaring this up comes to a positive difference, but it's basically the same in both groups. So now we want the sum of this, and this is our chi-squared, right? So our chi-squared is now the sum of 20.571 and 27.51. So this essentially adds now up to our chi-squared of 41.14. So at this point, probably the question whether this is significantly different is kind of a rhetoric one, because we said that our chi-squared value would be 3.841. So 41.14 is quite impressively larger than 3.841. So from that, and yes, we will reject the null hypothesis, and we are accepting the alternative hypothesis at a p-value of 5% at least, probably even more. Yes, this is this depiction, right? So this is how you calculate the chi-squared goodness of fit, and yeah, it's pretty simple, right? So essentially, what you do, you take the two groups, you map out the observed frequencies. You have observed 52 and 4. You map out the expected, which is with one nominal variable. Depending on your null hypothesis, it is, in most cases, if you assume there's no significant difference, you would essentially assume this to be 50-50. And then you basically compare your observed minus expected, you square it, and you divide it by the expected count. Gets you to this fragment and this fragment. You sum it up, you get to the chi-squared, and you compare it to your critical value. Easy, right? So now we're moving to the next chapter, the next part of it, which is a little bit more challenging. So now we are essentially coming to the chi-squared of independence. So now with chi-squared for independence, we're analyzing two nominal variables. We have again 6 steps of hypothesis testing. We identify the population distribution of assumptions. We state the hypothesis. We determine characteristics of the comparative distribution, critical values. We calculate them and decide based on the calculations. And again, the comparative distribution is again a chi-squared distribution. And the hypothesis test is chi-squared for independence because of 2 nominal variables. So the hypothesis is now, and this is where it's getting a little bit complicated, because it's easy with one nominal variable where you basically have, okay, so there's a disbalance and there's a higher count in one group or not. Because now you have, visually you can, numerically, you can say, okay, so it's higher in one group. But now what you learn is you're basically collapsing your insights on one-dimensional level. So you're basically saying, okay, I have now 3 groups in the independent variable. I have one nominal variable that is our dependent variable, that again a nominal variable. So now the only thing that you can say here is it is associated or it's not associated. So the null hypothesis will essentially say there's no association between your nominal variable on the row and nominal variable on the column. So the example that is given here is kind of a cute example. So let's look at this example. So we have here work from Trudel et al. In a recycling study, 159 people were randomly assigned to one of the three groups. 53 were given a paper cup on which their name was spelled correctly. 53 were given a paper cup with their name spelled incorrectly, and 53 were given a cup with no name on it. The participants had to choose whether to recycle the paper cup or throw it in the trash. Of the 53 people whose name was spelled correctly, 25 chose to recycle it. Correctly spelled and recycled, 25. Only 13 of the 53 people with cups in which incorrectly spelled names, and 14 of the 53 with cups with no names chose to recycle it. Now, this is 13, this is 14. The cells for this observed frequency can be seen in table 17.5. So we have 53 were given essentially this cup. So the sum is here 53 for each of those groups, right? It was a randomized study. So they were all randomized to receive either one of these name spellings or no name. So now we have 53 in each group. We sum this up now. We essentially get 52 in this group and 107 in the trash. So now what you want to quantify now is whether there's an association or not. And this is the only conclusion that we actually can draw with this test. So now here are the marginal totals. These are the marginal totals. And here's marginal total. And here, this is the sum of N3, N4, N6, 159. So these are 159 people. So now, as I said, we have on the column, we have our observed. On the rows, we have our trashed. So now we're doing recycling. Let's do concatenate this, this. So let's concatenate. You can put this together. Concatenate and this will give us. That's the one in between. So we can do this, no, this. I'll drop this in the chat in a second. Okay. So recycling correctly spelled the name, right? So now we can just put this down. Recycling incorrectly spelled name. Now we do. Bring this down here. We're gonna do concatenate. This is not trash. This is K3, and this becomes I4. Good. So now we have this. So I'm dropping this in the chat quickly. This is the code how you can quickly propagate this all the way down. So just to walk you through that, concatenate essentially allows you to put several fragments together. So this is the character entry. This is whatever entry the cell contains. With concatenate, you can merge them together. So here I said concatenate J3, which is recycling, and I4. So J3 and I4 resulted in recycling. The hyphen are implemented here in the quotation marks, and you separate this with a comma, and then you have correctly spelled name is essentially then adding this entry. So now this is this kind of it's maybe a little complicated doing it the first time, but it's logical, right? So we have the first entry is either recycling or trash. The second part between the two commas is the hyphen that are kind of manually forced in there with the quotation marks. And then the third part is essentially here, the row names, correctly spelled name, incorrectly spelled name, or no name. And you can then easily just pull it down. The next thing you need to do is you basically, you're just copying these entries and these entries. And now we have them in the same format as known at Heinzen. And we're naming this now observed. And this basically is consistent with the way they have done it. So we have now, okay, comes later. Okay. Okay, good. So degrees of freedom. So is this kind of, is everybody following along with the labeling? And now you basically just take the first column, then the second column. And now we have our observed frequencies here in one. So as for the degrees of freedom, we talked about it before. So the degrees of freedom chi-squared here are essentially, let's see. Okay. Okay. So the degrees of freedom here are essentially 3 minus 1 gets us df row. 2 minus 1 gets us df column. So degrees of freedom are 2 multiplied by 1. That's 2. Make sense? Any questions so far? Because now what comes next is a little bit more confusing, because now you need to estimate the expected, right? So when you are expecting, you will expect them based on the outcomes. So you know that 52 individuals have recycled their paper cup. So your observed is the same, you expect that you observed, you have observed, right? So this was your observation. This becomes your independent variable. But you expect that this based on the outcome. And this is 52 divided by the number of groups within your independent variable, which is 3. And this is 3. So this becomes then 17.33. And this being said, if we're looking this in, we essentially can just put it down. So now for trash, essentially we're doing nothing else. So for trash, essentially we had 107 paper cups. So our outcome here is 107. Let me do this. It's 107. And this divided by 3 groups gives us now 35.67. Putting this down again gives us the expected. And from here on, it's basically a stroll in the park, because it follows exactly the same outline as it did for the goodness of fit test. So essentially the only thing you need to do now is to calculate observed minus expected squared. Oops. Squared. So this is now observed minus expected squared. So that's this. And now the only thing we need to do is to divide it by the expected. And I'm just I just want to bring this formula over here. So this is again this formula, right? The sum of observed minus expected squared divided by the expected, and we're summing this up. And this is true for all of them, right? This is true for all these degrees of freedom. So the chi-square bill is built of all the degrees of freedom from the entire contingency table. So this divided by expected gives us the individual component. And the sum of this gets us again the chi-squared. It's the sum of this. That's 7.60. And now we have, we talked about, okay. So now we can essentially look at the chi-square distribution. No, not here. Chi-square distribution. We have 3 minus 1, 2, multiplied by 2 minus 1, 1 is 2. So we have degrees of freedom is 2. We're looking to test against a critical value of 5%, which is 0.05. So essentially we can now, so it's 0.05 and 2 degrees of freedom. And we have 7.60. And we are rejecting our null hypothesis, which has a critical value of 5.991. So these are the calculations as Nolan and Heinz have done them. This is 107. They're doing the same calculations, and they are rejecting again also the null hypothesis. It's considerably simple, right? So just as they are stating in the book and also on the slides, the critical part is really to know how to calculate the expected. This is really, this is where the money is. Everything else is a stroll in the park. It's just simply putting some formulas together. But it's really the concept and recognizing how to quantify the expected. And that's also what will be important for your final. So this is really what you need to know. Conceptually, you need to understand. So how do I quantify the expected? How do I do the calculations in principle? And there's not going to be much calculations that you will have to be doing, but it's important that you master the concept. Any questions so far? No? Simple, right? Very simple. Any questions with any of these calculations here? Let me know. Okay, great. So then we have the difference between the observed frequency can be labeled adjusted residuals. We are not calculating these, but this is how you would basically get adjusted residuals from your estimate on whether this is statistically independent or not. What you will need to calculate is Cramer's V, Cramer's phi, yes. Cramer's V or phi is essentially the effect size. So that's the calculated effect size for a chi-square test. So what you are doing to calculate this, so let's bring this formula over. So what essentially is meant with Cramer's V versus phi. So phi is actually the effect size when it is not multiplying it with DF rows and columns. So this is only for the goodness of fit chi-squared. For the chi-square test for independence, you need to multiply your sample size with the degrees of freedom for row and column. So in our case now, this is essentially calculated as, so we have Cramer's V is now square root of the chi-squared value divided by the sum of all entries. So this is the sum of all observed multiplied by 2, because that's our degree of freedom. Right. So now this grammar V, the effect size for this calculation is 0.15. So again, square root, open parentheses, M21 is our chi-squared, divided by our N, which is the entire sample size, the sum of all these entries, multiplied by the degrees of freedom, which essentially we can also get from, this is I11. We can also get it from there. Make sense? Yeah. I think it's considerably easy. It's really not that complicated. And the greater scheme of things, we've definitely done more complicated things. Okay. So if no questions, then let's carry on. So this is the effect size. The effect size essentially of 0.15. And again, here conventions, right? So there are conventions to quantify your effect size. And when degree of freedom, row and column, is 2, as was in our case, medium size is, oh, well, we actually have a small effect size. So we have 0.07 to 0.21. So with 0.15, we're right in here. So these are the conventions, and yeah. Any questions on effect size? So it's basically, it's determining, so we are testing that there is an association between the dependent and the independent nominal variable. And this is quantifying just in the same fashion as we did, for example, with a correlation coefficient. It's determining the strength or the effect size of this association. So what else is important? What would be an alternative approach? No, it's not an alternative approach. It's a visual way to determine that. So obviously, as you know, you have proportions, right? So these proportions essentially are determined by the counts within each group. So we have 2 groups. We have observed recycling, observed trash. This is our outcome. So now our proportions is now, I'm carrying this over. Our proportions essentially now are being quantified by recycling, trash. So correctly spelled name. We had here a count of 25, and we have a total of 53. This means that our actual proportion is 0.47. And here is a division by 0 because I didn't lock that in. So now this is 28 divided by 53. So this is 0.53. And the sum of this total is once again sum of P4 to Q4. This is 1. So it adds up to 1. So this being said, now we can basically go all the way down here with 24 over 75% with 26% and 74%. That's up to a total of 1. The total of 1 we read on it. Okay, good. But this is basically how you would calculate this. So you are within your categories of your independent variable. You quantify the relative proportions. And you're doing that for a reason, because you essentially want to depict this now as a bar graph, right? Because this is elegant how you essentially will be showing that, and you can easily do this. And now I just hope I'm doing this right. I'm not a big expert in bar graphs, neither am I an expert in Excel graphing, but I'll do my best. See, perfect. Okay. So you select the entire thing and select the whole thing from left upper to up to right lower tab, and essentially you get it's a bit total. Okay. So you have correctly spelled name. This is this column. So this is basically how you depict your data now with a proportion. Okay. And this is essentially the same as Norman and Heinzen shows here. We also have a legend. We don't. No, we do. We do have a legend. Okay. Proportion. You can depict these proportions simpler by not comparing them, or you can depict them comparing both groups. This is essentially how you would show that. So now remember that we had with the ANOVA, for example, we also got like this global overarching F score, which we used for hypothesis testing, right? The hypothesis that was being tested was that the groups are significantly different. So there's at least one group significantly different from another. That was the null hypothesis. That was the alternative hypothesis. It was the null hypothesis that all groups are not significantly different from each other and from the grand mean. So now, after we concluded that there was a significant difference, we would do so-called post hoc testing with either Takis on a significant difference test or with the post hoc Bonferroni testing, the POS testing. So there's also something that kind of is comparable for the calculation of proportions. And so now we need to build a little bit of a mental bridge. So when you have a probability of an event occurring, this probability is being depicted as either a proportion or a percentage, right? So when you say there's a probability that I will throw this cup in the trash rather than I will recycle it, this is not only probability, but can also be labeled as a so-called risk. There's a risk. Risk is essentially nothing else but a probability. So essentially, when you want to transform this now mentally to this cup I'm holding in, so you give somebody a cup, and the cup runs at a risk of 47% to be recycled when the name is spelled correctly, or runs a 74% risk to get thrown in the trash if there's no name on it. So with the idea that essentially if I want to save the planet and I want paper cups to be recycled, which hopefully we all want, and we all understand the importance of that, we will all hope that these will be recycled. So one way to approach this is to write somebody's name correctly on the cup, and by that increase the probability that the individual will recycle that cup. So that's essentially what the study meant to show, meant to suggest, I assume. I didn't read the study, but I assume this was like the higher purpose of the research. So how can we quantify that? So we want to quantify whether there is a probability of this being thrown in the trash over this being thrown in recycling. So let's assume, as a reference, we want to quantify the risk of this ending in the trash. So we have now essentially the worst case scenario is, let's say, let's assume, yeah, okay. Lowest probability of ending up in the trash is with a correctly spelled name. So we are adding this now. So these are all percentages, right? These are proportions. So now I want to estimate the risk of, we want to quantify a metric, a relative metric for each of the groups. How does this group compare to the risk of any random reference group or arbitrary reference group? So if I'm saying, okay, so I think my reference group, I want to quantify how much is the risk increase with not spelling the correct name on the cup, or with not having a name on the cup at all. So this risk increase can be quantified by calculating the risk, so the percentage of the respective condition divided by the baseline condition to which you're comparing it to. So we are having here with trash versus recycling. We have here a risk of 52. We want to calculate the relative risk of that paper cup going into the trash when the name is spelled incorrectly. This can be calculated by taking 0.75 divided by the baseline risk, which is 0.52 when there's no name on it. Or when there's the name correctly spelled on it, sorry. So what I can conclude now, so this is the so-called relative risk or risk ratio. If I actually, in epidemiology, you rather label it risk ratio. So what you can say now, based on this number, so obviously if that were the same and I divide this by this, my risk ratio is 1. So the 1 is essentially indicating that there's no difference in the risk. If I divide this risk by this risk, I use the denominator as my baseline risk. So this is my reference risk. So everything exceeding 1 indicates that my testing group, that this cell, this risk that I'm testing for, is 43% higher as compared to the reference risk. Does that make sense? Are you with me on that one? Because this is important for whenever you're quantifying risk, for example, in populations, and you're talking about death risk or risk of hospitalizations, you will essentially quantify the risk within certain groups in exactly that fashion. So this is done in epidemiology on a daily basis. So if you are now testing, if there's no name on it, is this risk actually also higher as compared to the reference group? You will see that there's no difference. Oh, barely. It's 3% less. So essentially, a possible conclusion that you could make is that the incorrectly spelled name enraged the customer so much that he actually was 3% more likely to throw that cup in the trash because he didn't want his or her name wrongly spelled for eternity on that cup. So that's one interpretation, for example. So, but nevertheless, if the name is spelled correctly, recycling is more logical. It is more and more common, more frequent. So there's a high probability of this cup being recycled. If it's spelled incorrectly, it's more likely to be trashed. If there's no name on it, it's actually also more likely to go in the trash, but less likely than when the name is spelled wrong. Interesting, right? So it's kind of a cute study to emphasize this point, but yeah, so essentially with the relative risk, you can actually compare each group that you want to compare with each other And you can also, and there are formulae for doing that, you can, we're not doing that, but you can also calculate 95% confidence interval about this risk ratio estimates. And by that, you can compare risks for the significant differences between each other. So, but again, keep in mind, one is the reference group, which is here. 1.42 is tested, is testing this versus this. 1.4 is testing this versus this. So you get a relative increase of the risk based on the division between the test risk and the baseline risk. Any questions on this? Fairly straightforward, right? It's really not that complicated. Okay. Oops. Okay, what else do we have? Oops. Okay. Quick recap. The most important thing here is really to determine observed versus expected. When you have one nominal variable, you do a chi-square test goodness of fit. So you basically you state the observed entries, the observed counts. You compare them to what you would expect based on your null hypothesis, which essentially was 56. You would expect 28 in each group. You square observed minus expected. You divide observed minus expected squared by the expected. The sum of this will get you to the chi-squared. In the same fashion, and this in the same fashion, you will map out the contingency table of observed group 1, group 2, and the groups of the independent variable. You basically get your 6 entries for contingency table with 2 degrees of freedom. Degrees of freedom are calculated by k row, which is 3 minus 1 equals 2, multiplied by k column, which is 2 minus 1, gets us to 2 multiplied by 1, which gets us to degrees of freedom chi-squared of 2. With the marginal total, you can now move on. So you basically bring them here from a contingency table format to a long format because it's easier to calculate. You basically calculate the expected as your observed total divided by the number of groups, assuming that then your individual frequencies, your individual counts are evenly distributed amongst all groupings of your independent variable. So this is 1733 in all 3 groups, or for the observed trash, 107 divided by 3, which is 35.67. So now using this to quantify observed minus expected squared gets us to 7.6 of a chi-squared, and to Grammar's V, that essentially is 0.15, which indicates a small sample effect size. Bringing this now in the format of conditional probabilities for each of those groups, you get probabilities that add up to a 1, which is here sum of P4 to Q4 adds up to a 1. Oops. Adds up to a 1. And these probabilities that you have calculated here for each of your cells essentially can be used to calculate the so-called risk ratio or relative risk, where basically you choose one of your groups and your outcomes as your reference group. And this reference group is your 1. whereas all other ones are essentially calculated with this in reference, coming to an increase in the risk. So it doesn't have to go. And by the way, if you, yeah, we didn't speak about that. Okay, risk ratio. RR is the acronym for relative risk. It always can go in the other direction. So if you take one no name as the reference group, and this becomes your one, you can also calculate it in the other direction. So if this divided by this would, for example, be slightly higher. So this is 1.03, whereas this divided by this is essentially now 0.72. So it really is determined by the chosen baseline category, whether this is depicted as an added risk, an increase in risk, or it's actually being calculated as a so-called protective factor. So when it comes to seeing a cup trashed rather than recycled, writing the name on the cup is actually a protective factor. And this is how you would look at it in epidemiology, for example, where, I don't know, stopping smoking is a protective factor to reduce lung cancer rates, as an example. So there are many examples that we could use in this context. But basically, the correct terminology is either it's an additional risk or it's a risk increase as compared to a protective influence, a protective effect, a protective factor. So this is the nomenclature that we would be using. Any questions on any of this? No? It's fairly important, and it's a very nice way of approaching the topic. So I really like the paper cup example because that's very nicely visualized. Okay, so if no further questions, then we are essentially concluding, ready to conclude for today. And that would have been our last formal class with new material. Next week on Monday, I'm going to do that Excel class. I will send out a Zoom invite. Please, if you have time, I would love for you to join. Interactive is more fun than doing this alone. And on Wednesday, I'm going to do a review for the final. And this will be at the same times. On the 7th, that's a Friday at noon in 2022, we will be writing our finals. It's the same format as we have had the midterms. It's longer than the midterms, and it's gonna be about all topics and chapters that we have discussed. And yeah, please do the sample quizzes, complete all assignments, and make sure that you have completed all comments on the discussion board entries. And yeah.
I have a question about the final.
Yes.
Do we have to go on Zoom, or the quiz is just going to be open?
No, it's live on Zoom.
It's going to be on Zoom, and then we do the quiz from there.
Yes, yes.
Okay.
Any other questions? Anybody? If not, have a nice evening. See you next week.
Thank you.
Thank you. Bye-bye.
Thank you.